Good morning, everyone. Here I'm Dr. Yasha Tayal. Here I'm going to talk about the superconductivity. So, in which I'm talking about superconductivity in a series of lectures. In the previous lecture, I have taken part of these many topics. From these many topics, we have discussed about what the superconductivity is, Meissner effect, dependence of critical temperature and critical field on each other, persistent current we have addressed the critical current, and then we have addressed the type 1 and type 2 superconductors. So superconductors are basically the materials which have zero resistance, so the current can freely pass through them. So this is possible at very low critical temperature, which is known as the transition temperature. So this was first observed by H. Camerlingh-Onnes in the year 1911. So resistance above critical temperature is, if say somehow it is in 0.08 ohms, which are observed for mercury. So it was found that it reduces to 10 power minus 6 ohms below at temperature below critical temperature. So pure elements, the critical temperature is very low, but if we use an alloy, a combination of number of metals, so this critical temperature can be raised, which increases its utility in various parts. Here we have studied about the dependency of critical temperature on critical magnetic field. So if we keep a superconductor in a particular magnetic field, how the behavior will be, which we have addressed here. In Meissner effect, we have observed that the field lines are expelled as the temperature is cooled below to its critical temperature. So no field lines are allowed. So this leads to one other behavior of superconductors, which shows that these are perfect diamagnetic in nature. That's why the field lines are expelled through the system. Then we have addressed the persistent current. If the specimen is hollow, then a particular amount of field lines is penetrated. So these field lines are penetrated in the specimen. Silsby's rules shows the dependency of superconductors on critical current at a particular critical magnetic field. So we are having three main parameters. It's current, critical magnetic field, and temperature, over which a superconductivity phenomenon is based. Either of three is above its critical, then the material will be in the normal phase. Certain numericals were addressed from these topics. Then we addressed the types of superconductors. So there are two types of superconductors, soft and hard. So for pure materials, the material goes under the type 1 superconductors, that's soft superconductors. For alloys, the material goes under the type 2 superconductors, which are known as hard superconductor, as the material do not lose its superconductivity property at even high magnetic field, when it is placed in high magnetic field. So these are the things we addressed. So this is the values we have addressed for various combination of alloys. Again, behavior of types of superconductor with respect to magnetic field and temperature we have shown here. So the current topic which we're going to address in this particular video lecture is properties of superconductor. So there are various properties of superconductors. So whatever we have addressed till now, those are also actually properties of superconductor. So if I talk about temperature, so that is also a property. If I talk about this critical magnetic field of material, that is also temperature. If I talk about this behavior on current, that is also a property. So material should have a temperature below its critical temperature. It should have below critical magnetic field. We have addressed this thing. So this is also actually a property, but still we're going to explore other property as well. So the value should be within in this range. So outside of it, material is in the normal phase. On the inside this case, the material goes in the superconducting state. So we address this. Now this is some typical basic concept also, which we can say it is a part of properties. Apart from this, we're going to have one more important property, which is isotope effect. I hope so you already know what an isotope is. So we're going to have elements with different isotopic mass, the same elements, then with the same number, atomic number. These are known as isotopes. So for certain such type of materials, if their atomic number is same but their mass is varying, so their critical temperature will also vary. So this was observed for mercury is a very common example. Mercury has isotopic mass which varies from 19.5 atomic mass unit to it varies mass varies to 203.4 atomic mass unit. So we found that the critical temperature for mercury varies at 4.185 Kelvin to 4.146 Kelvin. So here we can say that as the mass is increasing, temperature is decreasing. So this formula generated for this particular behavior was observed that critical temperature is inversely proportional to square root of isotopic mass. Or we can simply write it as, so this should be constant if we want to study a material with a combination of other elements. So this was a thing which was observed under the isotopic effect. Here it was further related with the uh, lattice vibrations. So how the mass is dependent upon the lattice vibration. We all know that the mass, atomic mass of an element do has a connection with the isotopic mass. And what it was found that we are having a Debye temperature of phonons. So whenever lattice was vibrated, the energy is liberated in the form of phonons. So this the Debye temperature, the temperature in Debye for phonons is directly proportional to the, again, so their power actually wasn't written, it is minus half, minus 1 in this form. So here it is in the same way as this form does. We're going to have for the temperature for the phonons also. And we can write it in the same way. If we're going to have in combination, we're going to study a number of elements in this form. So at the end, we can write that the critical temperature, the Debye temperature for nodes is directly proportional to the inverse of square root of isotopic mass. So, right. So lattice vibrations or electron phonon interactions have an important effect on superconductivity. So this actually give a hint upon how superconductivity is dependent upon electron phonon electron interaction. Electron interaction. So this is one of very important parameter which I'm going to address in my future lectures, in which we will study the Cooper theory, how the super electrons are formed or what's the band gap of superconductors. For that, we need this concept. So actually, so whenever the mass varies, the critical temperature is varied, and so and this is due to basically due to the lattice vibrations, which are basically due to the interactions among the electron in the presence of phonon field. So whenever a lattice is vibrating, so the energy which is liberating, that's a phonon, so that is also affected here. So we're going to have this effect. The other very important property for superconductivity is entropy. Entropy for superconductors, as we all know that super electrons are having zero resistance, which means definitely the uh, electrons which are below critical temperature, we actually term them as super electrons. So these electrons will be highly ordered. So when they're highly ordered, so entropy will be reduced. So if I'm gonna simply, I'm gonna plot the graph in between temperature and entropy per unit volume. So this is the behavior, say for example, for any normal material. So this is for normal material. This is a graph. Whereas for a superconductor, what's going to happen is, say for example, here is the critical temperature. This is the normal temperature. So the graph will go that, say for example, this is the for superconductors, this graph. And below critical temperature, drastically this value will reduce to zero. So this is the behavior for a superconductor. Entropy is rapidly reduced. For normal materials, the temperature does not drop so high. So we're going to have this kind of graph. So for superconductors, entropy reduces drastically. So as the resistance is zero, or we know that certain other type of theory happens in between electrons, we term them as super electrons. So we're going to classify in the terms of super electrons and your normal electrons. I'm going to classify here the theory of entropy in this term, normal electrons and super electrons. So the formula for entropy for super electrons and normal electrons as be the symbol for entropy. So for normal electrons entropy minus the super electron entropy is equal to minus mu naught Hc delta Hc by delta T. So now what's going to happen is that at as the temperature is equal to critical temperature. So what will happen is that critical magnetic field will be reduced to zero. So this whole value will turn out to be zero, which means that your all of these electrons will be transformed into super electrons. We're going to only have super electrons. So below critical temperature, when the temperature is less than critical temperature, we're going to have only and only super electrons. And these super electrons are highly ordered, so there won't be any disturbance. And as these are highly ordered, the resistance happens to be zero, right? So this is the thing, this is the property or the behavior for the super electrons. I hope so this part is very much clear from this particular point. And one more thing, you must have been knowing that there is a term known as coherence length. So coherence length tells about the degree of orderness or the distance up to which the two electrons, say for example, are ordered. So for superconductivity, below critical temperature, coherence length is of order of 10 power minus 6 meter. So this is for super type 1 superconductors in which we use pure materials. As we use the combination of different materials, this coherence length can increase, and so the degree of orderness can be extended to over a higher length, and that's why its magnetic field will also be over a higher range. So this is a very important property which actually tells about what will be the internal mechanism, what can be the internal mechanism happening, which leads to zero resistance, which this leads to zero resistance below when the temperature is below critical temperature. So through entropy we get a high insight, especially from entropy and the isotope effect. So we need to know about this electron phonon interaction, what the phonon field is, what's going to happen here. So this speaks a lot about the possibility of what's happening in this particular part. Now, the third property which I would like to discuss here is thermal conductivity. So thermal conductivity, which all know that this is the property which tells us about that how much energy can be transformed from one part of the system to others. But definitely as the resistance is zero for super electrons, which this will show that the thermal conductivity will be less for super electrons. So, say for example, this is a graph of a normal material, and I'm going to plot here the critical temperature. For super electrons, we're going to find here for super electrons, we're going to have this type of behavior. So this is for normal and this is for superconductors. The thermal conductivity we can see here, the graph is in this type. So here the super electrons, as super electrons does not interact with the lattice. So what's going to happen as entropy is very much like that. This degree of disorderness is very less. So super electron does not interact with the lattice below critical temperature. And so the super electrons won't participate in any type of energy transmission from one part of the system to other. So this will lead to very low thermal conductivity for super electrons, definitely below critical temperature. So because above critical temperature, there is no question of super electron. We have just normal electrons. So these are the three important properties of superconductors. Regarding the next properties of superconductors, we're going to have our next discussion. I hope so this video is quite clear. And the topics and the content of this particular video are taken from, again, Arthur Weiss's the book by Arthur Weiss's Concept of Modern Physics, and Solid State Physics by S.O. Pillai. Thank you so much for patiently watching this video. I hope so the content is found useful